Hello, everyone. Welcome back. Happy Friday. Um, it's time for Markov chains. There is a homework 6 posted. It went up kind of late. I'm sorry about that. Um, and although I was in the middle of doing something very exciting to me, which was to show the equivalence of the Poisson definition and the little o definition, I wanted to pause that proof to talk about some things that I realized you need for the homework. And then we'll come back to that. So what I'd like to start talking about today, what I'd like to start with are the two closely related ideas of superposition and thinning of Poisson processes. Thinning. We're going to thin it out. We're going to remove some of the arrivals and kind of have a lower rate process. Okay, so superposition, I think, is not at all surprising. This means if you add two Poisson processes, you get another Poisson process, and you get to add the rates. So the setup is I'm going to let N1 of T and N2 of T be two independent Poisson processes with respective rates lambda 1 and lambda 2. So independent Poisson processes with rates lambda 1 and lambda 2 respectively. And I'm going to define a new process, N of T, to be the sum. So I'm going to let N of T be N1 of T plus N2 of T. And so my claim is that this new process is a Poisson process, and its rate is you add the rates of the individual processes. So this is a Poisson process with rate lambda being lambda 1 plus lambda 2. This is super easy to show, especially I and double I. If we want to show that it's a Poisson process, we have to show, this is the proof, we need that n of 0 is 0. Well, n of 0 is n1 of 0 plus n2 of 0. And because those are Poisson processes, those are each 0. So yay, we get 0. The next thing to show is that we have independent increments. And by the way, I'm choosing to go with definition 1 for showing this. So independent increments. So for independent increments, I'm supposed to set up a lot of time points, T1, T2, T3, T4, and we're supposed to look at the differences of the numbers. But really, the entire concept gets across with just 3 time points. So I'm going to let T1 be less than T2, be less than T3, and I want to consider in this case, 2 increments. The increments n of T2 minus n of T1 and n of T3 minus n of T2. So these are non-overlapping increments of the process, and they represent the number of arrivals or jumps or whatever that happened in the time interval from T1 to T2 and in the disjoint time interval from T2 to T3. So this is going to be a little bit informal just because, I don't know, because it's a good place to be a little bit informal. There's other places I want to spend our formal brain cells on today. So if you look at like n of P2, oh, so here's the proof. I know I'm in a proof, so the proof within a proof. This is the proof of double I. If you look at n of T2 minus n of T1, then this is an N1 plus N2. You know, I'm being really sloppy here. And an N1 plus N2, evaluated at the different times. But we can group these together. So we have N1 of T2 minus N1 of T1 plus N2 of T2 minus N2 of T1. So that is one increment of our new process. And if we look at the other one where we have n of T3 minus n of T2, then we can write this as n1 of t3 minus n1 of t2 plus n2 of t3 minus n2 of t2. And so we're trying to compare or look at two random variables. These are all numbers and they're random variables. So I mean, what I mean by numbers is not a process. I mean, they're random variables. And we've got, so here's where it's a little sloppy. We've got that the N1 process has independent increments. So for example, we have that these are independent, but we also have that it was given that I hope I gave it. Yeah, it was given that the two processes were independent of each other. So that gives you, for example, that the upper left yellow circle is independent of this one. So this first independent I wrote comes from the independent increments for the first process. The second independent I wrote comes from the assumption that we're looking at two independent processes. And we have another term, but the thing I'm not showing formally is that if we have like X, Y, Z, W, I guess I should have come up with that W first. If these are all independent, I'm trying to say that X plus Y and Z plus W are independent, and I'm not doing it really. I'm not doing it formally at all, but we could. So let's do the interesting one, I think. So triple I, the whole Poisson thing. So I want to let like an S be greater than or equal to 0, less than, actually, I don't need an ordered S and T. Let's say S greater than or equal to 0 and T greater than 0. And let's consider the probability that N, the composition process at time S plus T minus N at S. I'm going to finish writing this, but I regret it, is equal to some K. We need to find this. And we need to show that this is a Poisson probability. But what I'm regretting is really what we want to show. I don't care about the probability. We want to show that this random variable N of S plus T minus N of S, we really want to show that this is a Poisson random variable with parameter lambda T. And lambda in this problem was given to be lambda 1 plus lambda 2, the individual Poisson process rates. And so this is, we're down to a random variable. When I put the brackets around it, I'm talking about an entire process. But when the brackets are not there, I'm talking about a random variable, which is actually the number of arrivals you've seen up to and including time t. So the thing I've circled near the bottom is a random variable, not a process, not really, as written. And so how do we get this from our N1 and N2? We get NS plus T minus NS equals N1 S plus T plus N2 S plus T minus the same thing with the S, N1S plus N2S. So we get N1 S plus T minus N1 of S plus the N2 stuff. And we already know, because those two random variables are coming from independent Poisson processes, we know that this is a Poisson random variable with parameter lambda 1, because it's our first process, and the length of the time interval is t. And this guy is another Poisson random variable with parameter lambda 2 times the length of the interval, which is t. So really the thing we're looking at that we want to show is Poisson is the sum of two Poissons. And we've already seen in class that the sum of Poissons is Poisson again, although we only proved it for IID Poissons. They both have the same lambda, but the proof would be the same. Because if you have like an x1 Poisson, I'm just going to say lambda 1. This is sort of an aside because I'm going to use moment generating functions and then there's a t in there, and I think the t will be confusing. So if we have two Poisson random variables with different rates, so this is a side calculation, and these are independent, the moment generating function of the sum is the expected value of e to the t times the sum, and that is e to the first guy times e to the second guy. And because these are independent functions, they're functions of independent random variables, you can break it up. And we have the moment, you know what we have. We have the moment generating function of the first one times the moment generating function of the second one. And I'm not saying you need to know these off the top of your head, but the moment generating function for the Poisson was e to the lambda, in this case, lambda 1, e to the t minus 1. And then the other one, the same thing, but with a lambda 2. And these things in the square brackets are exponents. So you get 1e and you get to add them. And so I'm going to add the two exponents, and I'm also going to pull out the e to the t minus 1, and we get e lambda 1 plus lambda 2 times e to the t minus 1, which is the moment generating function of the Poisson process with, not process, sorry, a Poisson random variable with rate parameter lambda 1 plus lambda 2. So the MGF for a Poisson lambda 1 plus lambda 2 random variable. So I did take it out of the process thing because our rates actually involved a t. And I usually, not that we have to do it, have a t in my moment generating function. So everything after this squiggly line was really just sort of a side calculation to say that if you add up two independent Poissons, even if the rates are not the same, you get another Poisson, and the new rate is the sum of the original rates. So applying that back to right above this squiggly line, the sum of these two Poisson random variables is going to be a Poisson with parameter lambda 1t plus lambda 2t. In other words, lambda 1 plus lambda 2 times t. And that's what we wanted to show. So let me squeeze that in up here. I can't even fit this, but right here I could say this has a Poisson, I still can't fit it, lambda 1 plus lambda 2 times t, which is what we wanted to show to finish off showing that the superimposed process really a sum. I think superposition sounds like it's much more than that. But the sum of the processes is another Poisson process. And you can picture, I'll rely on my pictures. My drawings are awful, but you basically have two processes evolving over time and jumping at certain times. And then another one, no, please, you know what? Don't ask me to put these together. But I didn't mean for them to look like the same times. But all of these times, these 6 times would go on a new axis. They're pretty darn close. I can't draw this. So we're going to have one step function, and you can imagine some of the steps being white and some of the steps being yellow, but many more steps, so a higher rate. Okay, so thinning is kind of the opposite. This means that you have a Poisson process, and for each arrival, you can go in and tag it as like a type 1 arrival and a type 2 arrival, or more generally, you can have K types of arrivals. And you tag each arrival with probability P1, P2 through PK. And so the result is that if we just look at the type 1 arrivals, that is a Poisson process that is thinner than the original one. So this is a case of taking a lot of steps and taking some of them out. So let me write that down. But using thinning and superposition together is a great way to do problem 6 on the homework. And maybe also, I don't know, problem 6 for sure. There might be another one that it's good for. So here is thinning of Poisson processes. So suppose that n of t is a Poisson process with some rate lambda. So I'm gonna like tag each arrival or label each arrival as type 1 with probability p, or type 2 with probability 1 minus p. And I probably should take advantage of like writing this more generally right now, but I'm gonna let you like it. We can easily have 3 or 4 or k. So we can have type 1 through type k, and then we'd have a p1, p2 through pk, and all of those p's would have to add up to 1. So if you let n1 of t be the number of, oh, by the way, tag each arrival independent of everything that's going on. So independent of, like, you don't have a higher probability of getting a type 1 tag because you had a bunch of type 1 tags. So I'm just gonna be real safe here and say independent of everything. So I'm gonna let n1 of t be the number of type 1 arrivals by time t. And then n2 of t, the number of type 2 arrivals by time t. And I claim that these are each Poisson processes and that the P it's a proportion. And we actually kind of take the right proportion of the individual rates to each process. So the conclusion here is that N1 of T is a Poisson process with rate lambda times P, and N2 of T is a Poisson process with rate lambda times 1 minus P. And I'm sure you can imagine how that would generalize. If there's k of them, I would have a lambda times a p1, a lambda times a p2, all of the p's. Yeah. Okay, I don't think we need to go through. I'm just going to do the part of the proof with the fun part, the Poisson part, the more challenging part. I think the others are pretty straightforward and boring. So let's prove that the third criterion for being a Poisson process. And I'm going to use definition 1. Oh, I want to say a little more than this. And N1 of T and N2 of T are independent processes. All right. So because I don't just want to find a distribution for the N1 process alone, I want to find the joint distribution and be able to say, hey, it factors, and I see the both of the Poisson things I want to see. So let's look at a joint probability, the probability that N1 of T is some N and N2 of T is some M. So these are processes that have been pulled out, have been thinned out from the overall process N of T. And so I'm going to compute this probability by conditioning on the value of the full N with no subscript of T process. So this is the sum as K goes from 0 to infinity of the probability that N1 of T is N and N2 of T is M, given that N of T is some K times the probability that N of T is some K. But if K is 8, and the n and m don't add up to 8, then this probability is going to be 0. There's actually only one non-zero term here, and that is when we take the term when k is n plus m. So take a second to note that. This is 0 if n plus m does not equal k. And so maybe you recognize that from the beginning and never bothered to write the full sum, but I wrote the full sum. So now I'm just going to pull out the only term that survives. Okay, this last probability here I know because n of t is a Poisson process with rate lambda. So this is e to the minus lambda t to the n plus m over n plus m factorial. And the rest of the stuff, this is, so we're going in, right? The events are arriving in our Poisson process in the n of t. And we're saying with probability p, you are type 1. With probability 1 minus p, you are type 2. So if you call type 1 success and type 2 failure, we're really trying to count n successes in a total of n plus m trials. So there's a binomial thing happening here. Out of, right, so independent trials, the same probability of assigning type 1 on every trial, and we're trying to count up the probability that there are exactly n in the n plus m. So this is n plus m, choose n, and then, what was I doing? P to the n, and 1 minus p to the rest of it, to the m, or if you're strictly following the binomial, n plus m minus n, right? That exponent would give you m up here. So this has nothing to do with whether or not you already have down the other binomial stuff we were talking about. I mean, I guess it does, but once you see this statement, you've got n plus m trials and you're labeling them success failure with probabilities independent of all the others, and it's just the probability of n or even m successes. Right. So what am I going to do with this? I'm trying to find, what did I start with? I started with this. I'm trying to pull this apart so that the result looks independent and also Poisson. And I know exactly what kind of Poisson I want to see, but I am going to do this kind of fast. So this is n plus m factorial over n factorial m factorial. And so I'm going to collect terms. I'm going to take, for example, this lambda t to the n plus m, and I'm not going to write this one down. I'm going to break this up as lambda t to the n, lambda t to the m. I also have like a p to the n and a 1 minus p to the m. So I'm going to put that p in here and the 1 minus p in here. And in the end, little massaging, not that much, we will get down to e. We will have just this one e and all the other stuff. But because I know what I want to see, I'm gonna break up this e because I'm gonna use the fact that I can write e to the minus lambda t as e to the minus p lambda t times e to the minus 1 minus p lambda t, right? And so I'm gonna try to see the two different Poissons and we'll get e to the minus lambda p t to the n over n factorial times e to the minus lambda 1 minus p t. Move you down. Lambda 1 minus p t to the m over m factorial. All those pieces are actually up there. And so I had two random variables and I was looking at them at the values n and m. And I have split it up into an n part and an m part. And these are both valid probability distributions. So, right, the N stuff is over here and the M stuff is over here. This implies that N1 of T and N2 of T are independent because as factors, and it gives us the result we want, that N1 of T has a Poisson distribution with parameter lambda pt, and the other one. N2 of T is Poisson lambda 1 minus p t. That is the only sort of artificial thing I did. So, right, like I took a p to the n and I combined it with a lambda t to the n, and those things are obvious. And because I didn't do the intermediate step, my intermediate step would have been to say that the result, if you combine everything up there, is this product and then an e to the minus lambda t. But because I wanted them to look like the two Poisson distributions, e to the minus lambda t is e to the minus lambda p plus 1 minus p t, which is e to the minus lambda pt times e to the minus lambda 1 minus pt. So that was a pretty artificial move in order to distribute this over here and here to see the two different Poisson processes. So I like to use these in tandem when I'm trying to answer questions about bug races. Yes, it's always bugs for me. Oh no, I have a better one. All right, this is just an awful example. So I wanted bugs and I didn't really want to deal with the word problem. So mosquitoes arrive to my front porch light according to a Poisson process. And I wanted to make this seem realistic by giving an actual rate, but I think it's less clear than what is what, if I plug in numbers, whereas if I keep the parameters, everything's good. So mosquitoes arrive to my front porch light according to a Poisson process with some rate lambda 1. And then independently, gnats arrive according to another Poisson process with rate lambda 2. Okay, so here's my question. What is the probability that the next arrival is a gnat? This is more than just a stupid example I'm doing right now. We're going to need this result in a lot of things going forward. So you won't always have to do all of this stuff. You can go right to the answer once you understand this. I would superimpose the processes and say I would superimpose them, and then I would try to figure out the p and 1 minus p I need to break them up back to the original processes. And that's it. So if you let, I didn't denote these, so I'm just going to say up here, this is the N1 process, and this is an N2 process. And so I'm going to let N of T, which is N1, I'm going to define it to be N1 plus N of 2, be the bug arrival process for all gnats and mosquitoes. And it, we know by superposition, is a Poisson process with rate lambda defined to be lambda 1 plus lambda 2. And then now, if you are trying to find the proportion of, the probability on each trial, a bug comes, what's the probability it's a gnat versus a mosquito? So I'm going to call that here. I'm going to call it little p. And so I want to thin the process to get the two original processes. So I want to thin this process, this big fat process, to get the originals That seems a little backwards and circular, and it kind of is. So I need P times lambda to give me the P is my NAT probability. So that's actually lambda 2. And 1 minus P times lambda to be lambda 1. Now, lambda is lambda 1 plus lambda 2. So this is what I need. And so we've solved for P. This is not going to be anything different. You're going to get that, not that we wanted 1 minus P, but 1 minus P needs to be lambda 1 over lambda 1 plus lambda 2. That's how these two numbers sum to 1. And this is the kind of tag probability for the gnats. The bugs are coming, and you label them gnats with probability P being lambda 2 over lambda 1 plus lambda 2. So you can kind of see that you are looking at a proportion. You've got a two Poisson processes, things arriving with certain rates, and you put them together so you've got a faster rate process. And to find the probability that any one arrival is of one type, you kind of want the proportion of rate that belongs to that process. Cool, right? So this is definitely like problem 6 on your homework. And I think I just couldn't find it scanning it so quickly. I think there might be another one where you'd want to do this trick of superimposing and then thinning. But going forward, this example was really generic. You know, forget the gnats and mosquitoes. It was two Poisson processes. And so the probability that the next arrival is a type 1 arrival would be lambda 1 over lambda 1 plus lambda 2. And you can use that result going forward if you just want to quote that. Love superposition and thinning. They are really awesome tools to have in your probabilistic toolkit. And they're really awesome tools for simulation. I am using this right now. I'm doing a project where I have chemical reaction networks. So I've got like molecules of a substance A, which can react at some rate to produce two molecules of some substance B. And then these could maybe go back and split with some other rate. And my assumption, as we're going to see, the exponential assumption is pretty central to Markov processes. It's the lack of memory. So I need to prove to you that we're going to see the exponential really for any continuous time Markov process on a discrete state space. But my point is that I have a whole lot of chemical compounds and reactions, and I am simulating them, and I am putting exponential times between the time to the next reaction. And so I could do this by saying the next reaction follows an exponential time with rate K1 plus K2. That's like superimposing these processes. And then thinning it out, I would say the next reaction is a 2B to A reaction with probability K2 over K1 plus K2. And I don't think I described that very well, but I'm using this in, I was going to say real life, not really real life, but in current research projects. Let me use this to give you a teaser. We are eventually going to get into Markov chain Monte Carlo simulation algorithms. And I work in an area called perfect simulation. And the idea behind Markov chain Monte Carlo simulation algorithms is you have some transition probabilities and you simulate things for a long time. And you want to know what that limiting distribution is. You want to know how the process is behaving in equilibrium. And so people simulate for a long time. You already saw this on one of your homeworks, but you might simulate out for 1 million time steps. And that's not even long for some processes. It's really process dependent. And so how far you should go before you should call it quits and say, I'm almost in equilibrium, and how much error you have when you do stop. These are really hard questions to answer in general. But in perfect simulation, I get to see infinity in a finite amount of time and have zero convergence error. And it is, yes, as cool as it sounds. And it will probably be one of the last things we do at the end of the semester. All right, back to definition 3, implying definition 2. And I don't want to take the time to write these out again, which would be really useful. These are two of the definitions for the Poisson process. Definition 3 was the little o definition, and definition 1 was the one that had the Poisson distribution in it. Definition 2 had the exponential distribution. So here I want to go from little o stuff to the Poisson distribution. And so this is what I hold up as one of many arguments to tell you that Poisson processes occur a lot around you in nature. Because if you define your process with definition 1, that's a really kind of specific thing you're defining. You're saying the number of arrivals between these two time points has a Poisson distribution. But the little o stuff is, to me, saying a lot. That's actually equivalent, but it seems like a much less structured assumption. The number of arrivals in a tiny time interval is proportional to the length of the interval. I don't know whether you buy it, but let's show that definition 3 implies definition 1. Was anyone going to say something? I thought I heard an unmute. I'm just going to show 3, triple I. Certainly, single I is exactly the same for both definitions. Double I in definition 1 was independent increments, and in definition 2, it's both independent and stationary increments. So, did I say 2, 3? Definition 3, double I, is independent and stationary increments, which certainly implies independent increments. So definition 1, I, is exactly the same as definition 2, I. And why do I keep saying 1 and 2? Definition 3I is exactly the same as definition 1I. And definition 3, double I, implies definition 1, double I. Let's look at 3. I've got little o assumptions, and I want to show that I get a Poisson number of arrivals in a time interval of some fixed length. So I want to show that the probability that the number of arrivals between some times s plus t and the lower time s being k, I want this to be e to the minus lambda t to the k over k factorial. And I want that to come just from little o stuff. Now, definition 3, double I, says our process has stationary increments. So definition 3, double I, says it's okay if we only show the probability that n of t equals k is this. It says that we can just look at the probability that n of t is k. It's just an interval of length t from 0 to k. And I'll just remind you that double I of definition 3 says the increments are stationary. So any interval of length t will have the same probability. So this is equal to this according to definition 3, double I. And we are assuming definition 3 here. Let's do this. What the heck are we going to get a Poisson process out of this? I'm going to start with the case where k is 0. And let's look at this. The probability that the number of arrivals by some fixed time t is 0 is, I want this to be e to the minus lambda t, and that's it because the rest of it goes away. So let's do it. Consider a small and actually vanishing little increment h, little h that's going down to 0. And let's look at the probability that n of t plus h is 0. This can be written as the probability. So right, I've got like time 0, and I've got a time t plus h, which is just a little bit bigger than my time t. So if the number of arrivals at time t plus h is 0, that means the number of arrivals at time t is 0, and the number of arrivals in the next little increment of time, not t, is 0. And both of these are 0. So using definition 3 double I, which is the independent increments, I get to break these up. Using definition 3 triple I have a little o expression for this guy. So by definition 3 triple I, I'm just going to recap from the beginning. The probability that n of t plus h is 0 is the probability that n of t equals 0, which is what I'm trying to solve for, times 1 minus lambda h plus little o of h. That was the part 3 of definition 3, one of the things that were stated there. I'm going to multiply this out. And I'm going to do a little more all at once. So I'll have this p of, let me not, I have enough time, I think. I have p of n of t plus h is 0 equals p of nt equals 0 minus lambda h times the probability n of t is 0 plus a little o of h function times the probability n of t is 0. So this, because there's no h in this, is a constant times a little o of h function. And we talked last time about how that's still just little o of h. You multiply a little o of h function times a constant, it's still little o of h. And let me remind you that f is little o of h if the limit as h goes down to 0 of f of h over h is 0. Okay, so I'm going really fast, but now I have to. So I'm going to move things around and write this as the probability n t plus h equals 0 minus the probability n of t equals 0 divided by h. This is equal to negative lambda probability n of t equals 0 plus a little o of h function divided by h. And that is not necessarily little o of h. Remember, h squared is little o of h, but h squared divided by h is no longer little o of h, because if you divide by h again, you get 1, and that's not going to 0. Oh man, I'm out of time at the best part. This is a derivative. It's actually a right derivative. And then we want to solve a little differential equation. And that's, I'll leave it there. So yeah, I'm not even writing this well. If I let h go to 0 on both sides, this is going to disappear. By definition of a little o of h function, this is going to turn into a derivative. So we'll have a little differential equation to solve. And I know some of you are already seeing where the e is coming from. Cool. Thank you. Have an awesome weekend. And we are done.